So we're going to solve here another first order linear differential equation. And whenever we're doing this, the first thing we want to do is put it into standard form, right? So my standard form, I would isolate that dy dx. So I've got dy dx equals x squared plus 3y over x. So continuing, we already did this in a previous example, but we can unadd that fraction. X squared over x gives us x, and then I've got 3 over x y. So I'll subtract that, 3 over xy. I've got dy dx minus 3 over x times y equals x. So in this case, my p of x is negative 3 over x. My q is simply x. So now that we've had it into, or put it into standard form, we can derive our integrating factor. And I proved that in a previous example, but the integrating factor, v of x, is defined as being e to the integral of p of x dx. So in this situation, my integrating factor is going to be e to the integral of negative 3 over x dx. So I'm going to take the piece we have in our exponent and come over here and just do some scratch work. So in this case, we're dealing with the negative 3 integral of 1 over x dx. That's negative 3, the integral of 1 over x is the natural log of the absolute value of x. All right? So here, subbing that back in, I have e to the negative 3 ln absolute value of x. Using properties of logarithms, that's the same as writing e to the ln x, then raised to the negative 3 power. And what we know is when you exponentiate a log and they're the same base, those bases, or the base and the logarithm will cancel, and I'll just end up with x to the negative 3, or we could say v of x equals 1 over x cubed. So this is what I'm going to use as my integrating factor. So the next thing we do here is we take that differential equation in standard form that we started with, which was dy dx minus 3 over x times y equals x. And we're going to multiply the entire thing by that integrating factor, 1 over x cubed. So when I do that, I have 1 over x cubed dy dx minus 3 over x to the 4th y equals 1 over x squared. So I've distributed that there. And so the reason we did the proof where we determined what our integrating factor would be is because this creates the reverse of the product rule. So looking at what we have here, we've got this x function, derivative of y, minus the derivative of the x function times y. So we picked that integrating factor just magically so that if I take the derivative of this, I end up with that. And then similarly, the derivative of y with respect to x is dy dx. So the whole purpose of doing that proof was to show you how we could pick this magic v, determine how we pick the magic v, so that this always works out on the left-hand side to be the reverse of the product rule. So what we can do now is I can say that the left side of this equation is the same as saying, well, this is the derivative of 1 over x cubed times y. and that's equal to 1 over x squared. So to continue moving along, we would integrate both sides. Integrating the left, integrating the derivative, those are inverse operations. They're going to cancel each other out. I have 1 over x cubed y equals the integral of 1 over x squared dx. So now I'm going to continue to the next page. I've rewritten my problem, so we'll continue on. I'm going to integrate on the right, and in order for me to integrate that, I'm going to rewrite that as x to the negative 2 dx. So we continue along integrating. I've got 1 over x cubed y. When I integrate this, I get negative x to the negative 1 plus c using my power rule. So this is the same as writing 1 over x cubed y equals negative 1 over x plus c. Wanting to isolate or move that x away from the y value is going to help us to get it into standard form. So I'll multiply on both sides by x cubed. And doing this, I've got x cubed times negative 1 over x plus c. And so normally, a lot of the times when we're dealing with multiplying by a number, we don't have to multiply that by our arbitrary constant c, because it's just a constant value and we know what it is. But in this case, this is a variable. We don't know what it is. So we're going to distribute that, and I've got negative x squared plus x cubed times c. And this is true for any x value greater than 0. This represents our general solution. So that's what we would be looking for as our answer there.